This example asks us to find the radius and height of a cylindrical soda can with a volume of 354 cubic centimeters that minimizes the surface area. And you can understand why a company would be interested in doing this. Indeed, they want to provide a certain volume of soda, in this case 354 cubic centimeters, but they also want to save cost on materials, so if they can minimize the surface area while providing a consistent volume, they can maximize profits. But this result is a little surprising. Let's take a look. Well, as with any optimization problem, the first thing to do is to draw a picture and work off of that. So let's draw a picture here. Okay, so there's our soda can. Let's call the radius r and the height h. And let's see if we can define our goal here. That'll help us define our objective function. We want to minimize the surface area. Right, so we always want to pull out the thing that actually tells us what we want to do. So minimize the surface area. This means we need an objective function that gives us an equation for the surface area. So let's see here. Do you know what the equation for the surface area of a cylinder is? Well, it's essentially we add the base and the top together. So what's the area of a disk? Well, that's pi r squared, and there are two of them. So that gives us 2 pi r squared plus the area of the sides, right? This side, this part that goes all the way around. Well, if you cut that open, then you and unroll it, you essentially have a rectangle. The height of it is h, and the base of it is the circumference here of the circle, right? We're imagining cutting this thing and unrolling it. We get this rectangle that gives us sides. The base of it would be the circumference of this circle, which is 2 pi r. So thus the area of the sides is 2 pi r h. Okay, there's our objective function. The problem is that it's in two variables. So we go back to our problem and look for some kind of constraint so that we can write this only in terms of one variable. And there it is, a volume of 354 cubic centimeters. So our constraint is the volume, which we know is the volume of a cylinder, pi r squared h, is 354, which we can now solve for h. So h must be 354 over pi r squared. And I can tell this is already going to get a little bit messy. Once we have that h, we can plug this in all the way over here and get this s only in terms of one variable. Plugging that in gives s then must be 2 pi r squared. That doesn't change. But then we have plus 2 pi r, and then h was 354 over pi r squared. Okay, well, we get a little bit of simplification here. The pi's cancel and one of the r's cancels. And this is the thing we want to take a derivative of. So let's clean it up just a little bit. We can factor a 2 out to the front, though that's not really necessary, leaving us with pi r squared plus, how about 354. I'm going to write that as r to the negative 1 there, so it's easier to take the derivative. Okay, then we can take our derivative. S prime is then, okay, the 2 is still hanging out. Again, you could do this without factoring that 2 out and get the same result. Pi r squared, the pi is a constant. Derivative r squared is 2. So we have 2r, that is. So we have 2 pi r plus, make that minus 354 over r squared. All right, and that's what we want to set equal to 0. Note that we do have a case here for a critical point where r equals 0, but that's an absurd case of a 0 radius, which would then require an infinite height to get any kind of surface area whatsoever, so we'll toss that one out in this case. Setting this equal to 0 gives, let's see, 2 pi, we can just disregard that main 2 in the front there. We have 2 pi r equals 354 over r squared. Multiplying up by r squared gives r cubed equals, how about 354 divided by 2 pi, 4 divided by 2 pi, which then tells us r cubed is 177 over pi. And I know it looks terrible, but there's a nice result at the end, believe it or not. So then r would be the cubed root of that. Cubed root of 177 over pi. Okay, so there's our radius. That's not the particularly interesting part of this example. What is interesting is when we go to look for the height, and we'll do it in a special way. So let's see what happens here. We have the height then equals, well, remember the height is 354 over pi r squared. But I'm going to approach this in a very special way. Watch this, and then at the end the result will be worth it. So we have height equals 354. You could just solve this flat out and forget this step that I'm doing, but I'm going to do this like this. How about pi r cubed, and then we have an r up top. I basically multiplied by r over r. Why would I do that? Well, it simplifies things when we go to plug in this r. Now when we go to plug in our r, we have 354 times the cubed root of 177 over pi, and I swear this is going somewhere, all over pi, and then r cubed is then 177 over pi. Okay. Now, here we go. We have some cancellation. Pi and pi cancel, and 177 and 354 cancel, leaving 2, which is 2 times the cubed root of 177 over pi, which is technically our height. That's not the interesting part, but this is actually 2 times radius. So technically our answer for the height is 2 times cubed root of 177 over pi. That's not the interesting part. The interesting part is that this thing is equal to 2r. Well, why is that interesting? Well, note that if the height is 2r, then our cylinder is this perfectly squat little thing where the height is exactly equal to the width. Right? Imagine what that soda can would look like. It would be kind of like sometimes you see like a can of chilies or something in the canned foods aisle that's about that shape. But soda cans are not that shape. Why not? Well, it turns out that when you create a soda can, you want to double the amount of material on the top and the bottom for structural reasons so it doesn't break through there. So if you look at minimizing cost rather than minimizing area, it turns out it makes sense to make it a little bit taller so you're spending more space on the sides than you are on the top and bottom, and that's how you get the soda can that we see today of those certain dimensions. So it's interesting to go back and rework this with the cost now, knowing that the bottom and the top, say, cost twice as much as the sides because it's going to be twice as thick, and you'll get a much more realistic dimension of what we expect when we look at a soda can.